So this line here is just tidying up a bit, showing that you know, by putting in the i's, you get the hermeticity condition. Therefore, I d dx is h, which is just short for Hermitian. All right. Now, what about the other case where your operator a hat is just d dx, not I d dx? It's just to give you a contrast, give you a feel for you know, why are some potential candidate operators Hermitian and why others aren't. Right? Just to give you a taste for one which is and one which is not. Okay. All right. Now, from the start equation in the previous session, which was the definition of a Hermitian operator, you know, the two integrals in overlap integral notation. If you plug in for a hat, you plug in this operator d dx. The left-hand side, you get this, right? So check for the previous session for the definition of a Hermitian operator, and on the right-hand side, you get this. Okay. Now, this and this are not always the same, and all you have to do to show they're not that this is not equal to that universally, you know, to show that it's not always true, all you have to do is find one counterexample. Remember, it's if you followed my finite groups course before, to disprove something, all you have to do is find a single counterexample. That's enough to disprove something. All right. Well, it may be not so obvious, but it's just given to you. If so, you have two functions, phi and psi. So if phi is this form, 1 plus x times e to the minus x squared over 2, and psi is 1 minus x, almost the same, e to the minus x squared over 2. You know, both of these are well-behaved quantum mechanical functions, physical functions, normalizable functions. I mean, they don't blow up at when x gets very large, because this term dominates this one. So as x gets very large, this goes down to 0 faster than this goes up to infinity. Right? So both these functions are well-behaved, normalizable functions for quantum mechanics. All right. So now with these two functions, calculate this left-hand side and calculate the right-hand side, and you'll find that you get different values. So you know, again, it's a homework exercise. So plug in for phi here. Now it's a real number, so phi star is just phi. So just written it out again. Just the whole thing's real now, real numbers. So just plug in phi and differentiate d psi dx, and you know, multiply the two, integrate the whole thing. You know, do it for homework, and you'll get minus root pi over 2. Okay. Now, if you do the same with the right-hand side here, again with the same two functions. Now, phi here, this is all real. So phi star is just the same as phi. So now you've got an entirely real integral. Okay. So again, for homework, calculate the value of this integral, and you'll find that it comes out to plus, not minus, plus square root of pi over 2. Right? So there's a difference in sign, and therefore this does not equal that, and therefore the operator d dx is not Hermitian. Right? d dx is not Hermitian. Alright, so we've sort of hinted strongly at this before with various comments in earlier sessions, but the fact that your Hermitian operators give you real eigenvalues and orthonormal eigenfunctions that makes them a very attractive candidate, well, representation for observables. Now, remember the kind of recipe as a quantum mechanic, the person who does quantum mechanics. You're very keen on the idea of eigenequations because they give you the eigenvalues which correspond to the discrete, quantized, measured values of the observable you're talking about, the physical quantity that you're talking about. So, so you need to know, well, you need to know how, because that's the hard part, how to choose the appropriate operator for the observable that you're talking about. So if you're talking about observable big A in general, then how do you find its corresponding Hermitian operator, A hat? Right? And you want it to be Hermitian because if it is Hermitian, it has all these wonderful properties like, you know, orthonormal eigenfunctions and real valued eigenvalues. Right? That's, you know, really nice. So it looks as though we're coming closer and closer to the generalization in quantum mechanics that for each observable there is a corresponding Hermitian, underlined, Hermitian operator. Right? So that's becoming you know, more and more reinforced, and one of our rules, if you like, one of our postulates in quantum mechanics, because it's just so valuable. And you know, we're just keeping more and more examples in the future where this idea of having a correspondence between an observable, you know, some physical, measurable physical quantity, and its corresponding Hermitian operator. All right? So that's what's been said here. Let me get my little chair. I nearly fell off the bed one time if you've been following every session. And I don't want to risk that again. All right. Okay, so that's what I've been saying here. That you know, to each observable there's a corresponding Hermitian operator. That's sort of the essence of it. Okay, now something a bit new. Introducing the concept. Well, it's a certain kind of Hermitian operator, but its format is a bit different. For example, it's not a differential like dBdx or something. It's a matrix, right? So this new concept, so from here onwards for a while, is about the concept, the idea of a Hermitian matrix. Okay? So I'll describe now what that is, you know, how you build one, how you make a Hermitian matrix. Well, you start with let's say we're talking about a matrix, a square matrix of size n, big N. So n, big N rows, big N columns, right? A square matrix. So take n, big N functions, just phi I, you know, quite general. Doesn't really matter what the functions are for the moment. Right? We're just defining what a Hermitian matrix is. Okay. So you just got n of these functions, right? Now you define a Hermitian matrix. So your matrix now is A, and the mth row. So the element in the matrix at the mth row and the nth